This is video 3 in the series, Distribution Within the House. In the previous two videos, we covered electron movement, different electricity types, the generation of electricity and its transmission across distances, and finally, bringing it into the home. Now we'll talk about distribution within the house. In this graphic, we have a distribution box called the service panel, or more commonly referred to as the breaker box. All electrical service for the house connect through this box to reach its in-use location, as they should. This is the safety point for your home. The service panel is usually located near the electric meter. However, depending upon the house, the panel may be located in a hallway or basement, or may even be on the outside of the house or in the garage. With the door open, what you're seeing is the main cutoff switch and the individual circuit breakers. In this box, the main cutoff switch is at the bottom. It might be in a different location in yours. Switch the main to the off position, and all electricity will be cut off in the house. There are two types of breakers in this box, single breakers and double breakers. Single breakers are for 120-volt service. Double breakers are for 240-volt service, such as the pool heater, water heater, air conditioner, and so on. You can recognize a double 240-volt breaker by the metal band connecting the two switch levers together. Now the question you might be asking is, what is a circuit breaker and why do we need it? As the name implies, this device is designed to automatically cut off the flow of electricity if a circuit develops a short. And by short, I mean the hot wire finds ground in an unexpected way. Early on in the use of electricity, we discovered that a short circuit creates a sudden rush of electrons to ground. The friction created by that rush can overheat the wire it travels through to a white-hot condition, resulting in a fire. To prevent that from happening, the melt-away fuse was developed, a device that is still in use today. In fact, you'll find them in your car and in many other devices. The fuse uses a piece of metal that has a specific melting temperature. Placed in the circuit path, if electrical flow becomes too great, the fuse heats to its melting point, which opens the circuit, stopping the electrical flow. When the fuse wire melts, it's called a blown fuse. The circuit breaker operates on that same principle. However, the circuit breaker is resettable and therefore reusable, whereas the blown fuse must be physically replaced. Here's an example of a short circuit condition. In this case, a frayed cord has allowed the hot wire and neutral wire within the cord to touch, creating a short circuit. This heats the wire to a dangerous level. Here, the same situation is shown in a diagram format. The breaker is closed and the current flows normally. It is the appliance that determines how much current to draw through the wire, and it will only draw enough to perform its work. Appliances, from irons to toasters to televisions, control the flow of current based upon their need. That's what makes the short circuit so dangerous. When the short occurs, the appliance is bypassed and control is lost. The breaker detects the condition and reacts to it by opening the circuit. When it does, it's called a tripped breaker. With that knowledge under our belt, it's time to take a look inside the service panel. There's a lot to understand, and it's important to recognize the component parts and learn your way around. Let's take it from the top. The service lines come from the meter and terminate in the service panel. The gray wire is the neutral, and the black wires are phase 1 and phase 2 hot wires. The hot wires are connected to the main cutoff switch, and from the cutoff connect to the hot bus. The bus is another name for a strip of conducting metal. The breakers snap onto the bus, making connection. The gray cable is the neutral from the utility pole outside. It is tied to a connecting bus bar. This is where the white wires terminate. And last, we have the ground bus bar. This is a separate ground that is connected to a separate external grounding source. This is where any bare copper ground wires or green ground wires terminate. Here are the things to remember. When the main cutoff switch is in the on position, the breaker bus strips are fully energized. Do not ever touch those. With the main cutoff switch in the off position, the breaker bus switches will be dead. However, the bare terminating screws for the incoming phase 1 and 2 hot lines will still be energized, so be careful. Never touch those. This is a photo of a service panel being wired up. I'll point out the components again. Here are the incoming phase 1 and phase 2 hot wires from the meter. This is the breaker bus, one for each phase. The neutral cable from the meter is here and connects to the neutral bus. At this point, let's review the different wiring sizes and the standard color codes that are used. I mentioned this briefly in video 1. Here are 4 wire examples that are used for wiring the house and the breaker panel. The difference between them is the gauge of the wire, which determines how many amps of current it can safely manage. The color schemes, both for the exterior jacket and interior wires, are industry standards. They give a visual identification of the wire size and its purpose. At the top, the white jacket designates a 14-gauge, 15-amp service wire. The outer jacket is stamped as 14-2 with ground, which means there are 3 wires within the jacket: a black wire, which is the standard color for the hot wire, a white neutral wire, and a ground wire, bare copper as you see here, or it could be insulated with a green cover. White is the standard for neutral, and green is the standard for ground. When the wire gauge number decreases, such as from 14 to 12, it means the diameter of the wire is actually increasing. An increase in diameter means an increase in the number of amps the wire can support. A yellow-jacketed cable identifies a 12-gauge wire for service up to 20 amps, mainly used for microwaves and refrigerators or any other 20-amp requirement. Those are appliances that have a startup demand for more than 15 amps, but have a running demand of less than 15 amps. A large wire is required to accommodate their start. The orange jacket indicates a 10-gauge wire supporting up to 30 amps, used for air conditioning, clothes dryers, and such. Both the 8 and 6-gauge wires are jacketed in black. They can support up to 45 amps and 60 amps respectively. 8-gauge wiring is used for the stove, double ovens, and such. As you can see, the jacket color tells you a lot about the service it provides. And inside, the color scheme for the hot, neutral, and ground remain constant for all gauge wire. These are the common 2-wire with ground examples. However, there are other configurations available to meet other needs, such as under the sink in the kitchen, where a dishwasher and a garbage disposal require individual service. To meet that requirement, it's more cost-effective to make one cable run to serve both needs. For those circuits, you'll find a 14-3 single-jacketed feed, as you see here. Again, the white jacket indicates a 14-gauge wire for a 15-amp service, but within, it provides an additional wire, red, which is the second hot wire. Here's a graphic showing how it's used. Each duplex outlet is serviced by a separate circuit, which is fed from the service panel by a separate breaker. Now let's take a look at the endpoint termination of the wiring. These are the switches and the outlets. As you can see, there's a multitude of different styles with these endpoint devices. These devices are manufactured following standards specified by the National Electric Code. However, there is some leeway given in their application within the home. Builders are allowed to manage their cost of installing the electrical service as long as the end result meets code. For example, the code does not require a separate circuit breaker for each outlet. The code allows a number of outlets to be protected by a single breaker. Given that leeway, you'll find that typically all the outlets within a room work off the same breaker. Also, it's common for a single breaker to service the outlets in more than one room at a time, such as bedrooms. The same applies to lighting, and there's nothing wrong with this approach. It holds down the cost of buying the home, and it's safe. For an outlet, there are 3 connections to make: the hot wire, the neutral, and the ground. And just as you see in this graphic, the connections follow a standard. The face of the outlet presents 3 openings for the plug to be inserted. The longer vertical one on the left is the neutral. The shorter vertical one on the right is the hot wire. The semicircle one is the ground. This is known as a polarized configuration and is the standard for all modern outlets. Each outlet is rated for how much amperage it can carry safely, just like the wiring that will supply it. Seen here is a 120-volt AC outlet rated for 15 amps of current. Although not visible in the graphic, its rating is stamped on the metal support housing. Here is a 20-amp rated outlet, easily recognized by the T-bar configuration of the neutral plug slot. For every polarized outlet, there's a polarized plug to match it. Here are some examples for 120-volt service. With a semicircular ground plug, it can only be inserted into the outlet in one direction. Same for the plug with a wide blade. It will only insert into the neutral connection of the outlet. Assuming the outlet is wired properly, a polarization match is guaranteed. Now we'll look at the wall switch. Again, there are many styles. The most common is the toggle switch and rocker switch. Functionally, they are the same switch. They're identified as a single-throw, single-pole switch. That means they can only turn on or off with a single movement. It's called the throw, thus the single-throw switch. The term single-pole means they switch only one hot wire. And just like the outlets and wiring, they are rated for the amount of amperage they can handle. The common household light switch is rated for 15 amps. Here's the house wiring graphic again, showing the power from the service panel breaker going to the switch and from there to a light fixture. Expanding on that, this is how the circuit would be wired. The neutral wire is not connected to the switch, but is passed through the junction box to the ceiling junction. The ground wire is connected to the switch and is then continued to the ceiling junction. It is the black wire that connects to the switch. The lead from the service panel connects to the bottom screw of the switch. The black lead coming from the ceiling junction connects to the upper screw of the switch. Only the black wire is switched. Switched off, and the bulb is off. Switched on, and the bulb is on. Here's a diagram of the electrical flow. Switch closed, the circuit is complete, and the bulb lights. Switch open, the circuit is open, and the bulb goes out. This brings video 3 to a close. A lot of information has been presented in the first 3 videos, and I know it can be a lot to absorb. However, they will provide you with a foundation for understanding electricity that will aid you in working with it safely should that need ever arise. In video 4, we'll cover the practical application for making minor repairs. Thank you for watching.